Titan's dense atmosphere and chemistry mimics the hydrological systems on Earth and is thought to be home to methane-based microbial life forms, compelling scientists to explore its unique environment. But a 3-year journey outside the sanctuary of our blue planet's magnetosphere into the constant influx of solar wind and radiation is dangerous to say the least. So how do we beat the sun? Well, the first line of defense is the outer structure, typically made of metals like aluminium and lead. Incorporating lightweight carbon nanotubes, which are electromagnetic wave absorbers, into the outer layer would mitigate the effect of high-frequency EM radiation. CNTs can also store hydrogen atoms within their structures, which attenuates incoming neutrons, a form of secondary radiation. CNTs will also be able to reinforce the structure of the outer layer to withstand a 3-year mission without adding weight, minimizing launch costs. Protecting the crew in their day-to-day activities like sleeping can be achieved through protective sleeping bags constructed from water and hydrogenous low-density polyethylene, which exhibits good flexibility and hence comfort. A tessellating hexagonal structure constructed from it, with water pockets 1 to 2 centimeters thick like this, was chosen to allow a low perimeter to surface area ratio, minimizing the amount of polyethylene needed. The water would be sourced from present resources aboard the spacecraft and recycled after use. The individual hexagonal pockets contain individual valves that open to allow the water to flow and fill up the blanket through a primary inlet, then close to form separate hexagonal pockets, minimizing water wastage in the event of leakages. Having the individual crew members surrounded by shielding in this way, rather than the whole sleeping pod or living area, encompasses a lower volume, decreasing the required mass of materials. All this is fine for steady levels of radiation, but during solar maxima, when solar flares emit sudden torrents of solar energetic particles, a lot more shielding is needed at relatively short notice. An existing method is to build a radiation shelter surrounded by stowage bags to increase the mass. Extending this, to provide an additional layer of protection, we could encompass the radiation shelter with a structure made of graded Z shielding. This type of shielding can protect against the proton-rich environment as well as secondary radiation. The principles of origami are currently being investigated in aerospace applications. Structures like this would need to be highly collapsible to occupy a low volume in storage on the spacecraft. In this scenario, a rectangular prism shape could be used, one that is able to be swiftly flattened into a low-volume flat plane with ease. Carbon nanotubes, modified sleeping bags, and origami can protect us against harmful radiation, but future advancements in material science and other fields can bring about even more sophisticated and unprecedented methods of achieving this.